But we're going to practice these four for the antiderivative, and then we have an assignment that I'm going to post on Google Classroom. I'll probably give you about a week to do it because this would be a test assignment. I'm not exactly sure how I'm going to grade it. I'm probably not going to grade it exactly like I would like a normal test, given the circumstances, how long this unit has been, and so forth. It will go in as a test grade. I think I'm going to be a little bit more lenient. I might curve it and so forth. And then for the people who are here today, I might offer maybe some incentive for that assignment. I'll announce that kind of at the end of the stream. But we'll jump into it. So the last part that we did was the antiderivative, which is going to be important because that is going to be a main focus of... okay, awesome. So I know. Now we have at least 3 here. Like I was saying, this is going to be a main focus of our next unit. It's really going to be all about the antiderivative and stuff like that. Although we're probably not going to be calling it the antiderivative. We're going to be calling it what it really is, which is called integration. So we'll see kind of what that is very soon. And really what an antiderivative does. I mean, right now you can go backwards with a derivative, with functions, but it actually has a real practical geometric meaning that we are going to focus on. And then for these antiderivatives, all we just got to do is, just do that. Just go backwards with it. And then if we have to find the function, like in number 4, we can do that. So let's see. We have f prime of x. I'm going to just write it, because we have a square root symbol, and then for the square root symbol, we just want to rewrite it with an exponent. So it's 4x to the 1/2 plus 5x squared. Once you rewrite it, you are ready to take the actual antiderivative. So it's f of x. If you remember, the first step is to add the exponent by 1. So add 1 to the exponent. You also leave a space here because you're going to have to multiply by something. When you add 1 to 1/2, you get 3/2. And then you multiply the coefficient by the reciprocal of that, which would be 2/3. And you can clean it all up at the end. Plus, I'm going to leave a space. It's going to be 5x. This exponent's even easier because it just goes up to 3. Multiply by the reciprocal, which is 1/3. And then plus c. Don't forget that plus c at the end. So this becomes 8/3 x to the 3/2 plus 5/3 x cubed plus c. And that's fine. You can leave it just like that. You could rewrite the x to the 3/2. You could rewrite it as the square root of x cubed, which would be fine. That's kind of on you. That's preference. I don't mind how you leave it. When they're fractions as exponents, I'm fine with that. All right. Number 2. Rewrite. I mean, always identify what we need to do, which we have the cube root of x to the 4th. So we have to get good with our power over root. So this is power over root. It is x to the 4/3 minus 7. Now we can rewrite this in a different form. So this is going to be x. Nope, let me leave a space there. X. You're adding 1 to 4/3. If you're adding 1 to 4/3, I'll do it off to the side here. 4/3 plus, whenever you're adding 1, you just same number over itself with a common denominator. So 3/3. So this is 7/3. Minus, oh, sorry, I forgot the reciprocal part. 3/7. Which is easy because there's no coefficients. You don't have to actually multiply anything. And if it's a number, if you recall, if it's just a number and you're taking an antiderivative, all you got to do is throw an x in front of it. So it's 7x plus c. Number 3. 3 over the cube root of x squared minus 6x. Now, there's a few things you're going to need to do here before you start. So the two things I'm identifying that we're going to need to do is, well, number one, we see a square root symbol. We've known all along that that's not 100% helpful. And then on top of that, it's in the denominator. So this is kind of showing we're probably going to have to do negative exponents here because we're going to have to bring in the numerator. We don't want to take an antiderivative when there's something in the denominator. So I'll take two separate steps to rewrite it. So it's going to be 3x to the 2/3 minus 6x, but I'm going to take an additional step to raise that x to the 2/3 to the top by making it a negative exponent. Keeping the 3 there, x to the negative 2/3 minus 6x. Now it's in a good form, which we can take an antiderivative quite easily. So raise 1 to the exponent. I'll leave a space there. So 3x. Negative 2/3 plus 1 is positive 1/3. Take the reciprocal. You get 3 over 1. So you're going to have 3 times 3. Minus. Leave a space. 6x. 6x to the 1, so it goes 6x to the 2. Reciprocal of 2 is 1/2. Plus c. Rewrite. 9x to the 1/3. Minus 1/2 of 6 is 3x squared plus c. And then the very last one. The very last one, we're going to find f of x, but because they give us this condition, I'll highlight it, because they say f of 1 is equal to 4, this is going to allow us to figure out the value of c and then plug back in. So let's do just that. So f of x is actually a pretty easy function because we don't need to rewrite anything. So it's 10x squared, and then take half of that, plus 2x plus c. So f of x is 5x squared plus 2x plus c. But that's where we have been ending. That was just a regular antiderivative, but because of that condition, when it says f of 1, so when x is 1, you get an output of 4. So it's going to be equal to 4 when you plug in 1. So f of 1, so anytime you see an x, we're going to plug in 1. So it's 5 times 1 squared plus 2 times 1 plus c. And that's all going to equal 4. So then we're just going to solve for the value of c. So this is equal to, which is 5 plus 2 plus c equals 4, which is 7 plus c equals 4. So c is equal to negative 3. That's the value of c. Then, last step, plug back into the original function. So the function is 5x squared plus 2x minus 3. That was the last part of this unit, which actually concludes our review for the unit. That actually concludes the entire unit, which means there's only one thing left to do, which would be the test to the unit, as I've mentioned. I actually forget... actually, no, I never printed this stuff out for you. So I'm assuming you don't have this. Just let me know. I forget, because I've been doing different things for different classes. I don't think I printed this out for you. No, okay. Which means I will put the assignment on Google Classroom. If you have a printer, feel free to print it out. If you don't have a printer, which I'm very aware that most students don't have access to one, You can, of course, just do it on a separate sheet of paper. Just open up the document on Google Classroom, read the answers, show your work on a separate sheet of paper. So I'll be posting this test. I'll give you a week to do it. So it's basically going to be like a take-home test. And I'm just going to post it in Google Classroom. I'll just say it's due on Friday. But as I said, I'm going to give people a little bit of incentive for, people who are showing up regular to these streams, because I do appreciate that, because it's the same people showing up, the same people not showing up. So if you've shown up this week, I'm going to allow you to omit 3 questions, which means if you run into a question that is difficult, you can just write omit, number 1. I'm going to give you 3 of these on the entire assignment. I'm not going to put that in the description of the assignment. So if you're here, you know to do it. If you're not here, they're just going to do the whole test. And then I'll grade it accordingly. So any question that you get stuck on, like number 1, I know is kind of a challenging one. It is, I believe it's, I think it's a related rate. But if you thought related rates were really hard, feel free to omit it so you don't need to do it. So my plan is I will get this on Google Classroom. If not today, definitely early tomorrow. It'll be there, and I'll probably give you the entire week, so Friday to Friday, to do it. And of course, you can ask me questions on these too. Even though I'm counting it as like a take-home test, where we're learning remotely, most importantly, I want you to know the material. So feel free to send me a message on Remind. I'll be sure to help you, whether I can help you through video, text, email, whatever. I will try my best to give you any help that you have. And it's pretty straightforward assignment. I think it's 7 multiple choice, and then there's going to be some extended response. But if you have the notes from the review, I think you should be just fine. But I'll say it one more time. You can get 3 omissions on questions. If a question is too hard, just write omit 1, omit 2, omit 3, and you don't need to do it. All right? So I will get that up as soon as possible, and I'll put that in Google Classroom, which I think is kind of fair, because I think we've only had really 1 assignment remotely, and this one is a bit of a bigger one, but I think we're due for a larger assignment, and that would conclude this unit. So I think that's all I have to say on that. And you might notice that's only 20 minutes in. I do want to jump into the next unit, which you should have. You got this probably a very long time ago. You should have a packet where this is the front page. So if you can take a moment, if you have to go and find it, please do so now. But we are going to start this one. If you have it on you, great. But I'll give you guys a minute or so to get that. Okay? Does everyone have it in front of them? Who is here? For the 3? I think 3 of you or 4 of you. Okay, got 1. All right, this is going to be a little intro into what we're going to be heading into, especially next week. So it's an intro to our last unit of calculus, and for anyone who you can't find it. Oh no. What I would suggest, it's not going to be ideal if you don't have it in front of you, because drawing this one by hand is a little annoying because of the graph. It's actually not too bad, because you know what graph this is? It is x squared, which is, it's a parabola. So, you can do this on a separate sheet of paper. If you cannot find it, I'll be sure to put it, I'll try to put the notes on Google Classroom as well, just so you have access to them. Do you have access to a printer? If you have access to a printer, I'll put it on Google Classroom. Okay. I just went to the school yesterday too. I think the last thing I'm gonna have to do is I'll have to go to the school. I'll have to print you out a new one. You would have gotten this like early April, maybe even earlier, because I printed this out really early and we haven't touched it in a long time. You would have gotten the physics packet with it too, so you might have it mixed in with the physics stuff. I'm not sure. But see if you can find it. If you can't find it by tomorrow, let me know. I'll go back to the school sometime next week and I'll print you out a new one. I don't know when you'll get it, but I'll make sure to print you out a new one. Alright, so like I said, if any of you are going into any kind of science, math field, anything close to that, you are likely going to be taking Calc 1. And this is usually the last thing you would do in a semester, which is integration. That is the title of this unit, integration. You hear the word integration, or if you're taking, if you're taking what we call an integral, this is all kind of based around the antiderivative. I've been using antiderivative a lot, but the reality is we typically would use what we call the integral. And the integral is going to have a special sign associated with it. So usually on a lot of calc textbooks, you'll see this funky looking sign right here, this like long S. That is the symbol we use for integration. And basically you can, for now, we can just kind of take that symbol as that is an antiderivative symbol. Because you'll notice we never really used a symbol for antiderivatives. We just kind of did it. It's usually because we would use the integration symbol. But we never really talked about what it really is, what it means, and stuff like that. And that gets us to the area problem. There are two major ideas in calculus, and we've spent much time going over one of them, which is finding the slope of curved lines. But we could also do the other thing, which is we have a shape like this, and what if we wanted to know the area to this shape? Well, there's no equation for this shape. This isn't a triangle because what we would call the hypotenuse is curved. So, and we know we could have any kind of curved line like this. We could have a function that looks something like this. It could be as complicated as it wants. But what if we wanted the area to this? Well, there's no equation you can look up to say, hey, what's the equation for a shape that looks like that? We don't, one doesn't exist. It's not like a rectangle, length times width. It's not a triangle, 1/2 base times height. All these shapes have just clear-cut formulas. Take some variables, plug it in, you have an area. With a curved line, it's going to get a little bit more complicated, and this is going to require the use of calculus. So the idea is, when we did this with slopes, if you remember we did it with slopes, we got points that got closer and closer together. And if you get 2 points that are really, really close together, and you could find the slope between those 2 points, you would find the slope. But, choosing 2 points wasn't good enough. So you would get closer and closer to the point, which is the idea of a limit. So you get closer and closer and closer to the point. So it's like the limit as this point approaches this, and that's kind of how we evaluated the what the slope of the line was. And that's why the definition of the derivative was the limit as x approaches I think it was 0, or sorry, it's h, sorry. So this might ring a bell from the previous unit. The limit as h approaches 0 of f of x plus h minus f of x all over h. And that formula, we went a little deep into that formula, figuring out, it's these 2 points getting closer and closer together, and then you can figure out the slope of a curved line using that limit. the area problem is going to be very similar, except you want the area, so what are we going to do? So these directions right down here is, we're going to use the simplest shape that we know, which is the rectangle, because the rectangle has the easiest formula to find the area, length times width. So it's going to basically say, if we just put rectangles under the curve, how accurate can our area be? And that's what we're going to do. It says use rectangles to estimate the area under the graph in the interval from 0 to 1. Use 3 rectangles that have a width of 1/4. Draw the rectangles starting from the left, completing the rectangle as soon as you hit this graph, the gaps under the graph, so left endpoints. So we can't start from 0 because we don't know how high to go. So we're actually going to start from 0.25. So right there. And what these directions are saying is you're going to make a rectangle. You go straight up. Once you hit the graph, you're going to stop. And you're going to make this rectangle that is 0.25. So it's going to go all the way to 5 here. So it's going to go across here. And you're going to have this rectangle that looks something like that. And it says make 3. So now we're going to go from 0.5 to 0.75, which is all the way over here. So I'm going to go up. Once you hit the graph, stop. You're going to go across. And then you're going to have a second rectangle. And then, of course, the last one from 0.75 to 1. We're going to have a third rectangle from here to here. And now it says if we can find the area of these 3 rectangles, that would be an estimation of the area under the graph. And now you might ask, well, why are we doing this? Because there seems to be a glaring problem. What about these areas in here? How come they are being excluded? We'll get to that later. Because you should be able to make an inference here that the area of these 3 rectangles is not the area under the graph totally. It's going to be far less. There's pretty big gaps that we are missing. We'll get to that later. But we got to find the area of these 3 rectangles. So we just got to do length times width. We know the width of all of them. 0.25, 0.25, and 0.25. But now we need to figure out the height of each one. But we have an advantage. We know that this graph is x squared. So we can figure out the height of each of these quite easily. When x is 0.25, how high does the graph go? Well, f of 0.25 is just whatever 0.25 squared is going to be. That's it. You're just plugging in for x squared. So 0.25 times 0.25 is 0.0625. And that's the height. So I'm going to put that, I guess I'll put that over here. I'll just put an arrow. So if I want the area to this rectangle, well, length times width. 0.25 times 0.0625. That's it. So the area of this rectangle is 0.25. Length. Well, I guess that's the width. Width times length. That's fine. 0.0625. And that's going to be equal to 0.015625. And that's what we're saying the area of this rectangle is. So I know these numbers are probably not the nicest to work with, but hopefully you get the idea. Now we're going to find the area to this rectangle, the middle one. And the middle one's kind of the same thing, except we just got to plug in to find the height. But notice the height it's from here to here which I'll highlight in a different color. So you can't plug in 0.25 into the function because look what the x value is, 0.5. So I want to figure out what 0.5 squared is. Well, that's easy. It's 0.25. So in fact, this rectangle, even though it doesn't look like it in our graph, it's actually a square because it's 0.25 by 0.25. So what's the area? Well, the area of that is just going to be 0.25 times 0.25, which is, I think we know it already, right? 0.0625. So the area of this is 0.0625. Which makes sense. It's higher than 0.01, as it should be, because that's a bigger rectangle. We just got to do it one more time. But now the new height is 0.75. So we got to do 0.75 squared. This one I don't know, so 0.75 squared. The height of this green height is 0.5625. And then we'll figure out that area. 0.25 times 0.5625 equals, let's figure that area, it's 0.14. 625. So 0.140625. That's the area of all the rectangles. So if we want the area under the graph, at least of the three rectangles, we have one solution to do. We will add them all up. So let's just add all of these up. So we get 0.015625 plus 0.0625 plus 0.140625. Add them all up and I get an area of 0.21875. Which seems like a lot of work to get an area, and it is. But now I want to take into account that problem. What about all those missing areas? How are we going to account for just that? We have all these missing areas where those question marks are. We need to take an account for them. So we have a few solutions. And the solution we're going to do is we're going to do the same exact thing, and it's pretty much the same directions. It says do the same with the following, but we're going to start from the right and then draw the rectangles going from right to left. So we're going to have 4 rectangles. But as I start from the right, I'm starting from 1. I'm going to go all the way up. And then I'm going to go from right to left. So now you'll notice that this is actually extending outside the graph. So the bottom one's actually going to overcompensate how much area there is. And then from there, probably can figure out what we're going to do. We're going to figure out the area of all these rectangles and then average the two together. So then we're going to do from 0.5, we're going to go across. So notice I'm making the rectangles going from right to left. And really, I got your message. Yes, I will make sure to do that. I will post this video on YouTube so you can view it later. And then lastly, 0.25 to there. Now hopefully I can get all this done in 6 minutes, so I might go a little quick, but hopefully you get the idea. And obviously this area, when you add all these together, is more than the area under the curve. Because look at the parts of the rectangles, these parts here is doing the exact opposite problem we had before. This area is going to be larger than the other area before. So we're going to figure out those areas. The first one's pretty easy, I think. These still all have a length or a width of 0.25. But now the new heights, just be aware where the heights are. They're from here to here. So you should be plugging in that height right there. And that's easy because that height is 1. And 1 squared is 1. So 1 times 0.25 is 0.25. So that area is probably the easiest of them. 0.25 times 1 equals 0.25. That's going to be the biggest of them. And we're just going to go through each one. So I'm going to figure out this height. I'm just going to figure out all the heights, and then I can figure out all the areas. So I'm going to do 0.75 squared, which is 5, or 0.5625. This is 0.25. And then 0.25 times, which is in there is 0.0625. Whoops. All right, so my areas, I got 0.25 times the 0.75 squared, which is 0.5625. The square, which is 0.25 and 0.25. And the smallest rectangle, which is 0.25 times 0.0625. I'm going to throw these all in a calculator. .140625, 0.0625, 0.015625. So that's each corresponding area. I know I did that very quickly. Usually I would not go as quickly through that. But all I found was the area to each rectangle by plugging into, again, and I found all those values by plugging into x squared, where I have the green part highlighted. That's how I figure out the height of each rectangle. Now I want to add them all up. So adding up the areas to all 4 triangles. So I got that plus 0.0625 plus 0.140625 plus 0.25, and I get 0.46875. But one thing we know about this number, that is over the actual area because of the rectangles extending over the line. So if the top one was smaller than the area because of the gaps missing, and the other one was bigger, what we're going to do is we're going to take the two and average them together. 0.46875. I'm going to add the 0.21875 and then divide by 2, and I get a final area, which is a pretty accurate answer to what we're trying to find, of 0.34375. Which is pretty close to the actual answer. So one of the, and I say close to the actual answer because that's not the actual area under the curve. I'll let you know right now that the actual area under the curve is 1/3 or 0.333. 3 repeating, and so forth. So why are we off by just a little bit, and how could we have gotten closer to the answer? So I'm just going to jump ahead and say we can make the rectangle smaller. If you include more rectangles, you close the gaps. And if you close the gaps, you become more accurate. So I think I have a picture here. Yes, right here. This is kind of what we did, the middle one. The one on the left is what we want. But what happens if we make the rectangle smaller and then we do the same thing? Well, all those spaces actually add up to a little bit of approximation of a closer answer. But what's the correct amount of rectangles to use? Well, the correct answer is you want to use infinite amount of rectangles, but you can't calculate infinite amount of rectangles. But we can make a limit, making the limit as the amount of rectangles approaches infinity. And that's literally what we're going to do, and that is what the definition of an integral is going to be. So you'll notice right here, we're going to get into this very complicated definition sometime next week. You'll see right, I have a circle over there. It says the limit as n approaches infinity. That's for the amount of rectangles. N is the amount of rectangles, and then we got the summation, which you learned last year, is we're going to add up all those rectangles together. We're going to literally add up an infinite amount of rectangles to get the most accurate answer, and we will get an exact value rather than an approximate value. So that's kind of what we're leading into in terms of integration. So we're right here. Just to give you kind of a little bit of hindsight what we're doing, and that this is what the antiderivative is going to do. The antiderivative, which is the integral, is going to allow us to find the area under curved lines, and this is the method in which it does. It creates these rectangles. We want to make an infinite amount of them, add them all up, and then all of a sudden we have an area. All right, I am 1 minute over, so I'm going to end there. Remember, I'm going to post up that Google Classroom. I'll either get it on this evening or early tomorrow morning. But we're all done for today. You guys enjoy your day, enjoy your Friday tomorrow, and then enjoy your weekend.